fun, there's actually a second fundamental theorem of calculus. Okay? And between today and tomorrow, these are really our last lessons of the unit. Okay, we're going to talk about the second fundamental theorem of calculus both today and tomorrow. Monday, we're going to do some AP problems in class, and then Tuesday and Wednesday will be reviews for our Thursday, Friday test. Okay, so we are finally seeing the end of Unit 4. I will let you know that after Unit 4, we have 3 units that are super short. Okay, I know all of our units have been fairly lengthy, but now we're getting into some shorter units, which will be nice. Things will move pretty quick. And before you know it, it'll be graduation. All right, so this is the second fundamental theorem of calculus. Go ahead and write it down. Things probably are a little bit screwy because of all the surveys that we've had. I don't have an official day when they're going to be February. Okay, turn to your table and talk about why this makes sense. The derivative of the antiderivative of f of t equals f of x.
Because they are inverses, they undo each other.
X minus a over
Because we talk about because that's kind of how they discovered calculus.
Oh yeah, you right. In the alphabet A. I don't know.
All right. Pod 5. Why does this make sense? Okay. We have the derivative and the antiderivative. Are those undoing each other?
Yeah.
Okay, they essentially are, right? Okay. We can go through. Don't write this down. Okay. If we were to solve this right here, we would find the antiderivative. Right? Antiderivative we make with a capital F, and we would evaluate it from a to x, right? So the fundamental theorem of calculus says antiderivative at the top value minus antiderivative here. Okay? Well, if we then take the derivative with respect to x, the derivative of the antiderivative goes back to the original, and the derivative of a constant is 0. So there it is. So without actually having to take the antiderivative and then taking the derivative, we just know that they are essentially undoing each other, like Grace said. Grace, I know you got nervous about saying that, but that's exactly what's happening.
Well, I thought it was too easy.
Write this example down.
Section touch.
You know the Fairly Odd Parents?
See the magic of nothing?
Yeah, they had a magic muffin and made your wishes come true. It was definitely the best episode. Or movie.
Okay, so coming back to our definition, A just needs to be any constant.
Huh?
That's what we have, right? 3 to x. So the derivative of the antiderivative from 3 to x of t cubed plus 1, all we got to do is plug x in. We have x cubed plus 1.
Sorry.
Okay, we do have to write the antiderivative as a different variable so that when we take when we do the derivative, or the antiderivative, excuse me, we throw x in. Okay, so instead of t cubed plus 1, we're going to throw the x in and it's x cubed plus 1. Why, you ask? Don't write this down. But if we were to do this integral right here, like if we were to do the long way, the antiderivative of t cubed plus 1 would be 1/4 t to the 4th plus t, and we would have to evaluate that from 3 to x, right? So now we actually get to plug in x. Okay, well then all of that is we're taking the derivative of, right? So when we actually do the integration, since our limits of integration includes an x, we now have a function in terms of x. So now we're taking the derivative with respect to x. Oops, sorry. But instead of having to do this every single time, we have a shortcut. You like shortcuts, right?
Let's dig into shortcuts.
What'd you say? Coley, what'd you say?
What's that shortcut?
Right into
Oh my god.
That's the shortcut. Why what?
E to the T to the 2.
Wait, that was literally the answer?
Oh my god.
The derivative and antiderivative undo each other, but it needs to be a function of x because we have to throw x in when we do the integration and then take the derivative with respect to x. So yes, it is as simple as e to the x squared. Where is the catch?
See, there's the muffin.
I just want to prove that I was right.
Here's the catch. Well, here's one catch. Write it down.
It's just right.
What's different about this one? Okay, this is x to a instead of a to x. And when our limits of integration get flipped, switched, whatever you want to say, what happens to our answer? Oh, so you do know that. Because on the quiz yesterday, I had a handful of you who did not realize that.
She said, so you do know.
Okay, so we do remember that When we swap our limits of integration, we would negate the answer. So this is just negative sine of x squared.
How do you know that you have to flip it? Like, couldn't x be like smaller than 7? Couldn't it be 67?
Well, x could be anything.
So why does it have to be?
She broke my dick.
So A is fixed. Okay, A is fixed, but x could be anything. So we're gonna keep it at the top. Okay, and it always has to be constant to x.
What if we have x to x? That's
Like negative x to x, then you'd have to break it up into 2. All right, here's another catch. Oh. Any guesses as to what will happen?
X cubed.
What did you say? Sorry, you both said something at the same time?
Or when it was just x, we just rewrote f of x, but now it's going to be f of x.
Okay, so first of all, we have an x cubed in there. So when we actually go to rewrite, t cubed becomes x cubed cubed. But that's not all. We are taking the derivative, and inside of our derivative is x cubed. What happens when we have a composite? Chain rule. So our answer is 3x squared times the square root of x to the 9th plus 1. Since we have something other than x inside, in this case it's the limit of integration, but since we have something other than x inside, we have to use the chain rule.
I feel like that's a really graph to look
What? Did you say?
at. It could be a neat graph. It's got a lot of
Maybe you should graph it.
shots off. Yeah, no, it's not. It's a little bit like a shape.
I was told you would hope, huh?
There's a little.
I was hoping for something.
Find the answer without me and check with the neighbor.
Yes.
Find the derivative of this antiderivative. The derivative of the antiderivative. It does matter. It's used with what?
Like before and after.
Oh, like the 3x squared?
No, like so
The cube is with the x, not with the cosine. Okay, Dylan, what do you have?
3x squared cosine of x cubed.
Like that? This guy gets thrown inside of our function and then multiply by the chain rule, 3x squared. That's the second fundamental theorem. Now, your book work is going to come from this. However, there's something that we need to go back and practice now that we know the first fundamental theorem of calculus. So you're going to have a few problems from the book and a few problems on a worksheet for a combination of one full assignment. Does that make sense? Okay. This is what your worksheet is going to look like. Go ahead and write this information down. Is it? Well, like a month ago.
I thought it was last semester.
It's been a long
Back in January, do you remember doing stuff like this? Okay, so talk me through it. What did we do to find f of 3? First, we needed to find
The derivative, antiderivative. Oh boy.
I like it.
Yeah.
Yes.
Am I right?
I like that.
Yeah, that's what I thought.
So we know that our function should be the antiderivative of the derivative, right? We need to go backwards.
Yeah.
Okay, taking the antiderivative, we go backwards. So if we have 4x as our derivative, we need to go backwards to the function. Which means our function is what?
2x squared plus
Plus c. Yes. So this is when I asked you to find a particular solution. So we know that f of 0 is 6. So if I were to plug 0 in for x, we should get 6. So c equals 6. Okay. Well, then that would mean f of x equals 2x squared plus 6. So we can go ahead and find f of 3 by taking, that's not a 3. To get this is what we did like the very first week we came back after winter break. Like the Christmas winter break, not the snow day winter break. Okay. Now, we know the fundamental theorem of calculus. Let me show you an alternate way of going through this. Before I do, are there any questions or clarifications that need to be made about this? So now, I'll call it Method February. So we know f of 0 and we're looking for f of 3. So we know that the integral from 0 to 3 of our function should equal, so this is the derivative, right? This is our derivative, right?
Yes.
So the fundamental theorem of calculus says the integral from 0 to 3 is the antiderivative at 3 minus the antiderivative at 0. So since this is f prime, antiderivative would be whatever f is. Do you agree? Okay. Since 4x is our derivative, then the function would be its antiderivative. Because we would go backwards, right? F prime, we work backwards to f. So the integral from 0 to 3 of 4x, which is our derivative, would be its antiderivative of 3 minus its antiderivative of 0.
Yep.
Okay. So now we have a definite integral. We don't know f of 3, and we know f of 0 was 6, sorry. Okay. So this is 18 minus 0. And then to solve for f of 3, we would just have to add 6 over.
Why did you do 2 of 9 squared?
She was a step ahead of herself.
I was
Oh.
a step ahead of myself, yes. I knew it was 2 times 9, and so I wrote 9 instead of just thinking about it. Thank you. Colby, you know me too well.
Okay.
So here it's all one fluid motion. As opposed to method January, we had like find this, and then find this, and then find this. Okay, so Colby asks, is this one that we have to do? I would suggest practicing it, and I'll tell you which ones I think you should practice it on. Because if it were a situation that you had your calculator and you could not actually find the antiderivative, for example, if you had you can't take the antiderivative of this. You can't. You don't have the tools to do it. Okay? So you would have to use your calculator, but the only way to use your calculator is if you have a definite integral, which means you would be able to do this piece of it right here in this method, whereas up here we are taking an indefinite integral, which means we have to be able to find it. Okay? So I'm going to have you practice this method for like 5, 6, and 7 on your homework so that you understand how it is used for when you get to those parts. Okay. Would you like to set up one more example this way?
Yes.
Okay.
Wait, is this method January?
We're doing method February. I'm letting you write it down.
Yeah.
Okay, so if we want to find f of negative 1, pay attention. Our x values are 2 and negative 1. So we know that the integral from negative 1 to 2 of our derivative would equal the function value at 2 minus the function value at -1. This is the fundamental theorem of calculus. Our integral, our definite integral, equals antiderivative of b minus antiderivative of a. Okay. Just since, well, yeah, find me. What's our antiderivative here?
Or 2x.
Ah. And we know that f of 2 is 3, and we're finding this -21. Because this is 12 minus 32, -20. And then this is 1. So you have -20 minus 1. So f of -1 would equal, that's kind of tricky. I picked 2 problems with the same answer. It would not be.
Oh, okay. Yeah, I see.
Okay.
Sorry.
Anyone else need that explanation? Okay. So numbers 5, 6, and 7 need to be done this way. You also have a variety of book problems. If you want to do that on the back of this worksheet, you can, or you can do it in your notebook. I do not care.